we had a very successful partnership with Microsanj in pushing the thermal analysis to the next level. And that next level is to take into account the antenna, creating the link between thermal dissipation and electromagnetic radiation. That would foster a holistic vision where the integrated circuits, the packaging, the PCB and the antenna are treated in one single vision. And that single vision is very suitable for industrial testing because it is very fast and it is reliable. There is no interaction between the DUT and the measuring system, no interaction, no calibration, wirelessly doing. This is really a great deal. And we are building a system for pushing it for the industrialization of beamformers and testing. What you see here actually is different applications, sub-6 millimeter wave, and also beyond. What we have done so far is to characterize in time domain transient analysis of antennas. This is a front-end module in transmit and receive, and it is controlled through FPGA, the power varying between 5 to 30 dBm, and actually we have fall time, rise time, and the triggering is done through a VNA. So we have a demo actually in our booths at Microsanj and at EV Technologies where you can see in real time the current flowing through the antenna with the Roden-Schwarz system. It works also with Keysight very well. And one of the critical point is to have a unified vision where the reliability and the industrial testing are combined together in one single way. The second application is the beamforming. Today, there is no solution for beamforming in industrial testing. This is the only solution we know that can be deployed and that can allow mass production. Why? Because you can detect faulty antennas. In the middle picture, you see exactly detection of faulty antennas. This is an antenna in package solution. It was not possible before because you had to put it in an anechoic chamber, very costly, and the anechoic chamber also takes a lot of time to test one single device. Now it is possible with this system to be very fast and accurate in testing it for the fault time. It can be also coated on package it in a later. We have done some tests also at a higher frequency, 77 gigahertz. This is a module that has been built by TI for their K radar, 77 gigahertz. So we have been doing the test at 13 dBm power level, and we were able to see in real time the current flowing into the antenna part, and we did a good correlation between a measurement in the anechoic chamber and a measurement using Microsanj system. And the last example was the radar, where we do the correlation in real time for the receive and the reduction. This is a practical application where you can detect actually in the antenna elements the time delay to have the propagation through the antenna. And we have done that on spare antennas and antennas connected to the front-end module. So you can see really the current flowing through the antenna in real time. And this was for 0.3 watt. Really the power is not too high.
And I'll go over what thermal reflectance is, the spatial resolution, the temporal resolution, and apply this, how we can do this with our probe station and rack of equipment. And then we can do how we can apply this to over-the-air testing. And Sidina will go over this part. So one of the issues with thermal characterization, as devices shrink, the time constants also get faster. So the smaller the device, the higher the frequencies, and then also the faster the thermal time constant. So if you want to characterize the electrothermal interactions on this time scale, then we need to have higher spatial resolution as well as high temporal resolution. So we're going from microseconds or milliseconds temporal resolution to nanoseconds or picoseconds. And now we can go from the spatial resolution for infrared is typically around 3 to 5 microns. And with thermal reflectance, we can use UV light to get down to quarter microns, so 250 nanometer spatial resolution. And these are very applicable for new materials, so 2D materials or diamond, GaN devices, gallium oxide, many different applications for these new devices. So what is thermal reflectance? It's pretty straightforward. We use light to take a temperature measurement. So wherever the light hits, reflects back into the camera, and then that reflection is temperature dependent, and we measure that. It's about 1 part in 10,000 per degree C. And then we lock into that small signal, and so we can get the temperature response with using visible or near UV light now. So we have 10 times higher spatial resolution, and we can use the flashed or pulsed illumination, so we can flash lasers or LEDs down to picoseconds or nanoseconds. So it's the next level in thermal imaging to characterize these devices. And since it's a lock-in technique, we can go down to millikelvin temperature resolution. So the basic setup of the system, we have a pretty standard high magnification compound microscope with the detector on the top side, so we can have a variety of detectors for looking through silicon or for UV, so CMOS or InGaAs detectors. Then we can have multiple detectors on the same microscope. So we can have InGaAs on one and CMOS on the other. And then we integrate these into one microscope, and then the light goes in through the light input. We sample the top surface of the sample, and then we lock into that and calibrate that with a thermal stage to kind of put it all together and get a calibrated temperature map of your device. I think I'll go to the next one. So as compared to like the existing techniques that are out there, thermoreflectance has very high spatial resolution. So yeah, again, 10 times higher than infrared. The sensitivity, we're not using a cold detector and it's different physics, so it's still very good in the millikelvin range, but for the lower temperature measurements, lower power, the lock-in infrared is still very, very good. But since we can pulse these illuminations, we can go down to this picosecond resolution for transient analysis. And since we're using reflected light rather than being limited by black body radiation, we can measure metals very well without having to be limited by the low emissivity from metals. And then compared to like emission, if you're looking for failures, those emissions we're detecting those photons from recombination. So you don't really get any temperature information from that. You get for the location of the failure, but you don't get any of the actual junction temperature of that. And we can do this all without coating our materials as well. So in general, we use the infrared for the low magnification for package level characterization or kind of large die level. And then if we want to go to the higher spatial resolution, we use the thermoreflectance mode, and we can use 365 nanometers to measure GaN devices in the GaN semiconductor region. Or we can use the 530 nanometers, so green light, in order to measure on top of gold metals. So this is a nice example of showing the temperature profile and gradient inside the GaN channel for a standard commercial GaN HEMT. And this just shows for the FA application failure analysis, we can do, since it's a lock-in technique, we can just continue to integrate and get down to even less than a millikelvin temperature resolution with longer integrations timed. So this is for the FA application. So the longer that you integrate, the better the signal to noise is. And this shows an example for locating a failure in one of the gate oxides. So there's a small failure with 21 microwatts of power. If you do this with the infrared, we have a 5 micron pixel. So the defect could be anywhere within that 1 5 micron pixel. So with thermoreflectance, we can get sub-micron, 500 nanometer resolution and locate the exact location of this defect. And so why are transient measurements important? So they give you like the full image and the full details of your whole stack up of your device. So if you're doing different measurements with different devices with different die attach or different packages, when you look at the temperature versus time on a logarithmic scale, you can see the thermal impedance contributions for each different component. So each of these kind of steps correlate to a change in the thermal resistance, the thermal impedance. And then the time portion is related to the thermal capacitance. So the longer time it takes, the larger the thermal capacitance. So you can correlate these into a compact thermal model in order to fully characterize your device and kind of separate out the defect, the different the different portions of your device without having to guess about is the main contribution coming from the chip attached due to like a void, or is it from the chip that's causing most of the thermal resistance. And this shows the application for kind of relating to that. This is on the order of, the first one is on the order of 3 to 4 microseconds. And we have the contribution between the GaN on silicon carbide and GaN on diamond. And we can see that the first diamond device had a poor thermal interface between the diamond and the GaN region. And if you improve that, then we can see that the diamond has a very good thermal performance compared to the silicon carbide. And it's actually reaching steady state within 300 nanoseconds. Okay, and this is latch-up applications. For high-power devices, we can look at current filaments. So this is an example of like an ESD application, so a very high-speed single pulse, and you can actually see current filaments in the device. I'll give some time for Sidina for the actual applications. People are also like advanced packaging and 3D IC is becoming like more and more important as we try to integrate things and make smaller modules. So these time domain techniques can help localize the sources of heat or these defects or buried heat sources. So the time domain gives you the Z resolution in a 3D stack up. As a conclusion, we can see that the applications for sub-micron applications, as well as we can scale up to the antenna applications for larger scale. We can see, what we can see, it opens up a whole other dimension of investigation into your parts in the design for electro-thermal models and as well for like these antenna applications.